Hi guys, we're talking about practical electricity today. This chapter for the O levels or the N levels are pretty much the same across the streams. So if you're any student, combined science student or pure express student, this chapter's learning objectives will be the same. Alright, so there are a few objectives that we have to learn. Uses of electricity, measuring electrical energy, dangers of electricity, and the safety features in any home circuitry. So first, we'll talk about uses of electricity. We're going to talk about very simple applications of electricity. So in specific, we're going to talk about thermal energy and also light energy. So electricity can be used. We can convert electricity into thermal energy. So there are quite a lot of applications at home that uses this. For example, heater, iron, your bread toaster, your oven, all uses electricity to generate thermal energy, or rather it converts electrical energy into thermal energy. Now, for all these heating applications, what they have in common is that they will have a heating element inside all of this, and it's usually made out of nichrome. And the reason why we use nichrome is because it's a material that has high resistivity and can withstand high temperatures. High resistivity is important because when any electrical current passes through, then it will cause the material itself, in this case nichrome, to heat up very rapidly. So that's why we use these materials in our heating elements. Alright, so some applications: electrical energy to thermal energy in kettles, in irons, in radiators or heaters, or electrical hot plates. Now, the other application that we use for electricity is converting it to light energy. Of course, now it is not so common to use this light bulb, or the tungsten bulb. We usually use LEDs now in our home. So, but the reason we used tungsten in the olden days was because it also has high resistivity and high melting point. So you see quite a little bit of commonality with nichrome. The reason, because we want it to heat up very to a very high temperature, and this heating effect would then, as a byproduct, generate light. So that's how the old light bulbs used to work. So that's all that we need to know at the O levels for uses of electricity. The next portion we'll be covering is how does one measure electrical energy. Alright, so there are a few formulas that you have to learn for electrical energy. We'll cover them in a little bit more detail. Alright, so let's have a look at this. Now, it looks like there's really a lot of formulas here. You got power equals to work done over time, the voltage equals to work done per unit charge, and then you substitute, the current is charged per unit time, and then you get this formula. Now, it sounds all very complicated, but if you have a very good idea of what voltage and what current is, then actually this formula P equals to VI comes about very naturally. So let's say I have a circuit, normal circuit, two bulbs attached, and then I say that there's a 4-volt potential difference across this light bulb, and a 2 ampere current runs through the circuit. Alright, so you know, or rather if you don't know, then I will tell you the potential difference across the bulb is the amount of energy each charge has, or each charge gives to this bulb. So the amount of energy given by each charge, coulomb of charge. And current, the amperes here, is the amount of charge that passes by in the circuit per unit time. In this case, it's the same throughout the bulb, the number of coulombs passing by per unit time. Now, so if we talk about it, 2 amperes actually means 2 coulombs of charge passing by per second. 4 volts means I have 4 joules. Each coulomb has 4 joules of energy. So if each coulomb has 4 joules of energy and have 2 coulombs of charge passing by 1 second, it means very simply that the amount of energy given to the bulb is 8 joules. So 2 coulombs of charge per second, 4 joules for each coulomb. So in 1 second, I have 8 joules of energy. So that's how I get 8 watts. Now, so this comes very naturally, and therefore this formula is very easily derived just based on your understanding of what voltage, potential difference, and current is. But of course, if you have difficulty remembering, you think it's much easier for you to just remember one formula, go ahead. You can just remember that the electrical power is calculated by taking the potential difference across the bulb multiplied by the current running through the bulb. Now, there are a few different formulas that you will need to know to complete your understanding of electrical power and electrical energy. One of them is the power formula, which is the rate of energy or work done. So power equals to energy per unit time, and of course your V equals to IR formula. Now, there's this whole derivation, or just a quick recap. You also need to know the SI unit of the power is the watt. 1 watt means 1 joule per second, and also the unit of energy is the joule. Now, so these 2 slides covers just the whole derivation, but there are 6 formulas or 6 different formulas that you can use. Now, what I like to remember is I only like to remember formula 1, which is the power formula, energy equals to power times time, and 2, power equals to voltage or potential difference times current, and 3, I like to remember just this. And from these 3, of which 2 you already know from previous chapters, you can derive all 6 of these formulas. So P equals to VI, energy equals to power times time. I substitute P equals to VI into this formula, then I just get VIT. Power is VI, so VI times T. E equals to VIT. So this is the first 2 formulas, formula A, formula B, that you have to remember. Now, from here, I can substitute V equals to IR and replace V here with IR. Then what happens is I just have IR multiplied by I, which means it becomes I square R. The energy formula, just multiply by time. And then I just manipulate your V equals to IR, make it of the form I equals to V over R, and then substitute into here. So V equals to IR, I replace the I with V over R, then I will very easily derive this P equals to V square over R. If you're having difficulty, P equals to I square R, substitute I equals to V over R, so you get V square over R square multiplied by R, then therefore you have P equals, or rather you have V square over R. So you have derived this formula. And then again, to get the electrical energy formula, you just multiply by time. Now, what's the use of having 6 different formulas all talking about electrical energy and electrical energy and electrical power? It's basically because out of V equals to IR, if you are given any 2 of this, you can use the corresponding formulas to calculate either the power or the energy. So let's say I'm given V and I, then I know immediately I can just substitute into this to calculate electrical power. If let's say V is not given or not known from the question, I'm given I and R, then I can use this formula to calculate the power directly. Alright, so that's the use of having the 6 different formulas. Alright, just a simple calculation. 20 watt bulb, 10 seconds is just using your energy equals to power times time. This has very little to do with electrical energy. You can solve this using from your understanding of work energy power, the chapter on work energy and power. Now, things get a little bit complicated. So let's look through this work example. A bulb in the circuit is rated as 60 watt, 240 volts. Now, sometimes you see electrical appliances having this in the label or in the sticker somewhere, it says 60 watts, 240 volts. Now, what solution is correct for calculating the current flowing through the bulb when this bulb is connected to a 120 volt supply? Now, what does this sticker or this label mean exactly? What it means is that when my bulb is connected to a 240 volt supply, when my bulb is connected to a 240 volt supply, then the amount of power by the bulb is 60 watts. Now, this bulb is no longer connected to 240 volts. supply. So that means it is not getting 240 volts. So this label or this number is not exactly useful now, but it is useful for us to know and calculate the resistance of the lamp. So using one of the 6 formulas, P equals to V squared over R, I can calculate the resistance of the lamp. Why is it I can calculate the resistance of the lamp? Because the resistance does not vary with the voltage or the current applied through it. Alright, so I can calculate the resistance, and from there then I can use my resistance of the bulb, which doesn't really change, connected when it's connected to a 120 volt supply V. Then I can calculate the current running through it, 0.125. Now these two solutions don't work because what they did was they used 60 watt bulb and 120 volt. Right, but this doesn't really work because at 120 volt supply here, the bulb won't be giving off 60 watts of energy, 60 watts. Alright, so this formula doesn't work. I cannot calculate. Neither does this. If it's connected to a 240 volt, 60 watts, yes, the current given will be 0.25 ampere. But you are not connected to a 240 volt supply. You are connected to a 120 volt supply. So the next slide just tells you the reason, the working on why solution 3 is the correct one. Alright, now, so we calculated electrical energy, and then now I'm telling you that actually by right, energy is calculated using power times time. So usually in any case of calculation of formula, you are always told to go and change it to the base unit. So make sure there's no kilowatt, make sure that the time changed to second and not in hours or minutes. But there's one exception to that formula, and this is the exception. Whenever you're calculating cost of electrical consumption, you are required to use kilowatt an hour, meaning the watt you change it to kilowatt, the time you change the seconds to hours. Now this is the only formula in the whole syllabus that you don't really need to change to base SI unit to do the calculation. Now the energy therefore will then be calculated and in the form of a unit of the kilowatt hour, because it's kilowatt multiplied by hour. Now this kilowatt hour is also known in the O-level syllabus as 1 unit of electricity. Now why is it important, or why is it that we calculate electrical energy so specially using kilowatt hour? Because in general, most equipments or electrical equipments that we use are in the kilowatt hour or in the kilowatt range, meaning they are in the 100 watts to maybe about 2000 watts. So most of the electrical equipments are in this range. So it's easier as a smaller number for us to deal with. Also, electrical equipment, we don't use them in the time frame of seconds. I mean, most electrical equipment runs for hours and hours. Your TV, you can switch it on for 3 hours. Your laptop or your PC, you can switch it on for 4 or 5 hours. So it becomes easier to calculate when the numbers are not so huge like this. So if I were to calculate 1 kilowatt hour, that means I use an appliance that is rated at 1000 watts for 1 hour. In electrical energy terms, it's actually just 1 kilowatt hour. But if I wanted to calculate it in joules, I could. All I needed to do is just change it to 1000 watts. 1 kilowatt is 1000 watts. Change the hours to second, which is 60 seconds, and 60 minutes, multiplied by 60 minutes, and you get such a big number. So these numbers are generally quite big. So it's very difficult for us to deal with them. So we use 1 kilowatt hour to use in calculation of cost. Now, if you have seen your electrical bill at home, it will look something similar to this. Alright, so they will tell you it's 100 and you use 145 kilowatt hour this month. The rate 0.2729 or about 28 cents per kilowatt hour. So then in calculating the cost that you use per month, it's just the kilowatt hour 149 times this rate of 27 cents, and you get the amount about $40. Yeah, so that's how we deal with calculation of electrical energy in dealing with cost. So just a simple example, 1.5 kilowatt electrical coil heater is used for 2 hours. Calculate the amount of electrical energy in kilowatt hour. So all you need to do is take energy equals to power times time. The power, leave it in kilowatts, so it's 1.5. The time, leave it in hours, so it's 2 hours, so it just becomes 3 kilowatt hours. So the second part, they ask you to calculate A in joules. Then all you need to do is, in the process of calculation, instead of leaving it in kilowatt, you change it to watt. And time, instead of leaving it in hours, you change it to seconds. So it's 1500 times 2 hours, 60 minutes for an hour, 60 seconds for each minute. And you get this amount. So this is exactly equals to 3 kilowatt hour. Now, this is common phrasing in O levels. 1 unit of electricity costs 25 cents. So this is actually 1 kilowatt hour. So 1 kilowatt hour is 25 cents. So I use the amount of energy equivalent to 3 kilowatt hours. I multiply by 25 cents per kilowatt hour, you get 75 cents. So the cost of using this 1.5 kilowatt electrical coil for 2 hours is 75 cents. So when we talk about sources of electrical energy, I'm going to discuss the type, what it converts from, what kind of energy or where the source is from. We discuss the efficiency of this source of energy, the cost involved, and also the environmental effects. So we'll talk about solar energy first. Solar converts light to electrical energy. Now, it can be highly efficient when it's bright. Newer and newer technologies nowadays is making the conversion a little bit more efficient. So it's a higher percentage of the light that is being converted to electrical energy. There's very little wastage. With newer technology as well, excess energy can now be stored in batteries, so there's no wastage there. The problem with it is that there's quite a high cost in manufacturing, but of course, as we are pushing more and more for solar energy, the prices is dropping. But of course, once you have installed it, the cost of energy is free for as long as there's sunlight, then you'll get free energy, right? The problem is that, of course, there's a requirement for land space. So in Singapore, quite a landlocked country, we have very little land space. This one is not it's not that possible because we don't have that much space for us to put solar panels up. Alright, hydroelectric electricity, it converts the GP of water into electrical energy. Now, it's efficient because we can generate the electricity when we want to. We can release a valve, water can flow down, and then I can generate electricity. Now, the cost involved, there's quite a big cost in building dams. It's quite a big mega project, and also on top of that, you need a maintenance cost yearly that can be a lot. Now, of course, ecosystems are greatly affected by the building of dams. Upstream, you have a lot of flooding, your river systems are affected. Downstream of the river, you have a lot of basically you have no more water there, so any ecosystem that thrived on the river downstream will be affected. Alright, wind energy converts kinetic energy of the wind to electrical energy. It varies, of course, depending on the wind conditions. It's getting the cost of building this wind turbines are getting lower and lower with improved technology, and of course, for as long as there's wind, the energy is free. Some notes against it that has been brought up is an eyesore. I don't really agree with this because I think it looks quite great, and of course the main trouble is that it also requires a lot of land for you to build. So in countries like Singapore with limited land space, then this is not really that feasible as well. Alright, nuclear energy, it converts nuclear to thermal energy, then to electrical energy. It's very highly efficient because it only requires a small amount of radioactive substance, and then you can generate quite a lot of electricity. Of course, any excess energy can then be stored in batteries. Cost involved, it's quite high because you have to build the infrastructure to harness the nuclear energy, and also with the disposal of the nuclear waste. Environmental effects, of course, radioactive material, once they are done, they need to be disposed of. Sometimes when it's not done properly, it can seep into the ground and down into the groundwater. Of course, other environmental effects are Fukushima and Chernobyl, you know that there has been leakages or failures at the nuclear power plants, which resulted in the release of the radioactive material. So these are some of the dangers associated with nuclear energy. Now, fossil fuels, the one that we are mainly dependent on right now, it converts basically chemical potential energy to thermal energy, which then we convert to electrical energy. It is efficient because our infrastructure is structured around fossil fuels. Everything is already in place. You just need to bring the fossil fuel over and burn it, and electrical energy is there. But of course, the cost is increasing more and more because, well, there's a decreasing supply of, there's a limited amount of fossil fuels. Environmental effects, air pollution, the main one. Also, in the mining of this fossil fuel, you basically destroy quite a bit of the, or affect quite a bit of the ecosystem where you are mining. Alright, so we're moving on to the next part, dangers of electricity. Now, there are two main dangers of electricity. I summarized them here, and they are basically shock and fire. There are some causes that will result in shock, and there's some that will result in fire. I'll discuss them in a little bit more. So, damaged insulation. Alright, so if you have very old wires, I used to have this problem when I was using some of my old electrical equipment. The wires get frayed, then you have the copper wiring being exposed. Now, when your insulating material is worn or damaged, then if you happen to touch the copper wire, there's a chance that you get an electrical shock. So this is one of the dangers. Exposed wiring due to damaged insulation can cause you to have an electrical shock. Now, for fire, basically, overheating of cables will result in fires. Now, overheating of cables can, the causes of them are basically these two: overloaded power sockets and use of inappropriate wires. So, in our household, many a times we have a lot of extension cords. So it is not recommended that you put an extension on top of an extension cord, meaning you have an extension cord here, then you put another extension here so that you can plug in another 3 more, then you have another extension here from which you can plug in another 3 more. So what is happening when you put too many into just one socket is that you're overloading the socket. It means you are drawing too much current from this just one socket. That means the cable that is supplying this may overheat. And when it overheats, then if you have any flammable materials around, then that will catch fire. Now, uses of inappropriate wires as well. So certain appliances that require high power, you in general need thicker wires. So if you look at it, your phones, they in general don't need such a thick wire. You just need a thin wire. While for your fridge, microwave, or your PC, you need in general a slightly thicker wire. Now, why is this so? Because in general, the thicker the wire, the lower the resistance of the wire. So when you have a lower resistance, in general, you have lower energy loss across the cable. So when you have lower energy loss, you have less thermal energy generated in the wire. So that's why you don't see very thin wires powering high electrical consumption appliance such as the fridge, because then you have quite a bit of thermal energy generated in the wire that is supplying, and that will heat up and that may cause a fire. So these two, overloaded power sockets, use of inappropriate wire dimensions can cause overheating of cables, which will result in fires. Now, damp environments. The dangers of damp environment is that it can lead to electrical shocks, because water is a good conductor of electricity. So whenever you have water, or your hand is wet and you're touching the wiring of an electrical circuit, it can provide a path for the electricity to travel through, because it is a conductor, and then you can get an electrical shock. So basically, in summary, dangers of electricity, there are two: shock and fire. Damaged insulation, damp environment will result in a shock. Fires can be caused because of overloaded power sockets and using inappropriate wires for the application you are aiming for. Now, the biggest chunk of this chapter is safety features in home circuitries. So we're going to discuss quite a bit of home circuitries. So this is the learning outcomes. So So some of the safety features in our home circuitries are circuit breakers, fuses, switch, earthing wire, 3-pin plugs, and double insulation. We'll go into a little bit detail into each of them. So a circuit breaker looks like this. In Singaporean homes, it's usually found near the main door. It looks something like this. So what is a circuit breaker? Circuit breakers are safety devices that will cut off the electrical supply to the home when an excessive amount of current is flowing through the wire. So this circuit breaker is usually at the mains before the house. So that's why it's usually found near your main door. So without circuit breakers, if there's a sudden surge of current, it can cause your home appliances to have excessive amount of current flowing through it, heating it, causing the electrical components to fry, or it can result in a fire. So circuit breakers, just take note of this. We'll discuss it a little bit more. They are also connected on the live wire. Fuses. Fuses have the same function as circuit breakers. They also prevent excessive current from flowing through. Circuit breakers can be reset after it trips, which means after it trips, all you need to do is to find whatever caused the trip. It could be an equipment, it could be a surge of electricity. Alright, then you can just flip the circuit breaker and your power is back on. But for a fuse, you must replace it. Fuses are also connected to the live wire. Again, we'll discuss this a little bit later. What a fuse is actually a short thin piece of wire encased in a glass metal tubing like that. If the current flowing it is much too large, the wire heats up and then it will cause it to melt. When it melts, then I have basically an air gap here. It's an open circuit. Alright, so no current can flow through. Now, where are fuses found? Fuses are found in your 3-point plugs. So if you have a 3-point plug, this is what it looks like. So just to briefly tell you so that we can discuss it a little bit later, your 3-point pins, there are 3 pins. They are the earth pin. The top pin is called the earth pin. The one on the left is called the neutral pin. The one on the right here is called the live pin. Now, you wire your circuitry like that. Your fuses are connected at your live pin. So the current has to go through the fuse, then through the live pin, then down to the equipment, and then back out through the neutral wire. Alright, and then the earth wire, we'll talk about it a little bit later on. We'll talk about other safety features. Now, how do I know what kind of rating of fuse to be used? Because basically, a fuse is just a short thin piece of wire. So the thicker the wire, the more current it can take before it melts. The thinner the wire, the less current it takes for it to heat up and melt. So knowing what kind of fuse to use is important in what kind of equipment you are using. So if you are using an appliance that requires or draws 4 ampere of current from the main supply, you cannot use a 3 ampere or 4 ampere fuse, because immediately when you switch on your equipment or your appliance, this fuse, 3 ampere fuse, will blow, meaning it will melt. The 4 ampere also, at 4 ampere current, it will melt. So the rating of a current, the current rating of a fuse means the current at which the wire or the fuse will melt. So I should use a 5 ampere fuse. Your fuse should be slightly higher than the current that is rated for, so that when in normal operation, 4 amperes of current is running through the appliance, 5 ampere fuse won't melt and won't blow. Now, it is not desirable to use a fuse rating that is way too high compared to your normal operation current. Because why? Even if, let's say, I can go up to 19 amperes. Remember, your appliance is rated or needs only 4 amperes for it to use. Even if my current goes up to 19 ampere, my fuse will not blow. So this safety device is not a useful safety device now. Likely your appliance will fry, your appliance will heat up, it will cause fire before the fuse will blow. So in general, when you're looking for a fuse, find something that is just slightly higher than the normal current that is being drawn when you're using the appliance in normal. Alright, just now we talked about why fuses and circuit breakers must be placed on the live wire. So before we talk about that even, we need to understand what a live and a neutral wire is. So I've drawn a simple mock-up of what most electrical circuits, at the very basic, will look like. Now, so this is something that is not unfamiliar to you. You have a battery or power supply. One is positive, one is negative. That's what you learn. And then it's connected to a resistor, in this case whatever resistor it is, your appliance, and then it's connected back to the negative terminal. Now in most of your housing circuitries or your electrical mains, the positive terminal is actually held, or at least in Singapore, is held at plus 240 volts. Now the negative terminal is actually not negative, so in circuitries at home is held at 0 volts. So the potential difference is 240 volts. So each coulomb of charge is given 240 volts. So what exactly is a live and a neutral wire? So a live wire is the one that is connected to the high potential terminal and then to the appliance. So this is the live wire. So anything along here, all the charges here, for each coulomb of charge, there's 240 joules or 240 volt potential. Over here, 0 volt connected to the 0 volt terminal. Now, so the one that is connected to the 0 volt terminal is the neutral wire. So this is called live because it is connected to the high potential at the live terminal. Now, so why are fuses connected to the live wire instead of the neutral wire? Because in any case, whenever the fuse blow, be it on the neutral wire or on the live wire, you will have an open circuit. If it blows here, I have an open circuit here, the current cannot flow through, your equipment stops working. Even if the fuse is placed here, it blows, your equipment will stop working. So why we place fuses on the live and not on the neutral wire is because I want to separate the appliance from the high potential. True that in both cases, once the fuse blows, that the appliance will stop working, or rather no more electricity will flow through. So there's a minimal risk of your appliance catching fire here. But when I place it on the live wire and it blows here, I separate it from the high potential terminal. Now, what's the use of that? Because in case your fault or what causes the surge of electricity is your live wire fraying and touching this. So what I've drawn here is the casing of your appliance. So if let's say your appliance is a metallic casing and the live wire is touching the metal casing, and you happen to come along and you happen to touch this metal casing. So if your fuse was connected to the neutral wire instead of the live wire here, then this appliance is still all at 240 volts. The metal casing is all at 240 volts. And if you touch it, the current will then flow down through you down to earth and you will get shocked. So that's why we need the fuse here. The reason is that I want to separate the appliance and anything I can touch, therefore, from the high potential at the live wire. Now, when we talk about fuses, we talk about switches. So switches basically is a electrical component that breaks open your circuit so that current will stop flowing. Now, you place your fuse before your switch in all situations because you want the fuse, the safety device, to break before anything that you can touch. So the switch is something that I can touch. It's something that you have to touch to switch on your appliance. So you want the safety device first, so in case of any fault, it is broken here. So anywhere you touch after here is all safe to be touched. If my fuse instead was here and it breaks here, and here there's still a circuit, if you happen to touch the switch, you can still get electrocuted if your fault is at the switch. So that's why fuses and circuit breakers go on the live wire. Your fuse comes first before the switch. Now, in any normal circuitry, there are 3 wires. So if you break apart your normal wiring, there will be 3 different wires of 3 different colors. one is a red wire, one is a green and yellow, one is a blue. So now, the live wire is color coded red. Red because the color of danger. Alright, it's connected to the high voltage or high potential terminal. This is the one that delivers your current to the appliance. Alright, your neutral wire is the blue one, it's the one that completes the circuit. I like to remember it because it's the color of the sky or the sea, neutral. I don't know why I think sky and sea is neutral, but that's how I remember it. So it provides this path so that your appliance can work. The earth wire is a low resistance wire and is connected to your metal casing of the appliance. Now, how it's wired? It will be wired like this. So the one with the fuse here must be connected to the live wire. So your red wire will go to the pin that is connected to the fuse. Your other one here is connected, the blue wire is connected to the neutral terminal. And here the yellow and green wire, the color of earth, is connected to the earth terminal. Now, it's very easy to remember the live wire because there must be a fuse here. So how do I differentiate between the neutral and the earth wire? I differentiate it because the earth pin is usually longer. So in any situations where there is a need for safety, your earth pin is the one that will make the contact first rather than your neutral pin here. So I believe this is the live, this is the earth. If I were to flip it like this, alright, so your earth pin is the one at the top, this is your live pin, and this is your neutral pin. Alright, so earthing. Why do I need an earth wire? So in situations such as this, where we already discussed, you need an earth wire to prevent anything from happening. So if let's say your fault happens here and your fuse fails to blow and you happen to come here and touch, there's a chance that you get a shock. But if there's a wire connected to the metal casing, which is the earth wire that is connected down to earth, then the current, instead of flowing through you, via the metal casing and through you, it will preferably go through the earth wire because it's lower resistance than you are. So it prevents you from getting an electrical shock. Now, the earth wire also has two functions because once my current flows here and down through the earth wire, there's basically no resistance along its path. Wires, zero resistance, connects down to the metal casing, no resistance, earth wire, zero resistance. So when resistance drop, V equals to IR, provided my voltage remains the same, where my resistance drop to almost zero, my current will shoot up. So when my current shoot up, then your fuse will blow. So this works, the earth wire works in conjunction with the fuse to keep you safe. Because once there's a fault, not only will your fuse blow because of the earth wire, there's also zero chance of you getting an electrical shock. So that is the function of the earth wire. Remember, the earth wire must be connected. It's a wire with very little resistance and it's always connected to the metal casing of your equipment. Now, the 3-pin plugs. Not all countries use 3-pin plugs. Singapore uses it. It's known as a safety plug. You have the fuse, again connected to the live pin, red wire. The earth pin, the longest pin, connected to the earth wire, and the neutral pin, the blue pin. Alright, so what about all those that do not have an earth pin? Is it not safe to use? Alright, so those that have 2 pins, in Singapore at least, they do not have an earth wire because they have something called double insulation. Now, a double insulation can be seen on appliances with this symbol. It looks like a square and a square. Now, what it means simply is that all your electrical components and cables are insulated from the outer casing, anything that you can touch. So, what it looks like, a label, it will look like this. A square and a square. This is a sign for double insulation, and what it looks like is this. You have a supply, you have a fuse, you have a switch, then you have your whatever electrical components of the equipment. So all of this is encased in another layer of plastic, So there are two situations. Either your whole entire casing that you can touch is made of plastic. So even if something happens and touch your outer casing, you won't get electrocuted because plastic is an insulator of electricity. Or there's another layer of plastic beyond your metallic casing or before your metallic casing. So even if your electrical wires fray and touch, you will be touching the plastic and not the metal portion. So this is what it means to be doubly insulated.